welcome back. My name is Greg Dick. I'm the Executive Director of Advancement and Senior Director of Public Engagement here at Perimeter Institute. In the spirit of respect and reconciliation, we acknowledge that Perimeter Institute is located upon the lands that have been inhabited by Indigenous peoples from the beginning. In particular, we acknowledge that it is situated on the traditional territory of the Anishinaabe, the Attawandaron, the Haudenosaunee, and the Neutral peoples. Perimeter Institute is located on the Haldimand Tract. After the American Revolution, the tract was granted by the British to the Six Nations of the Grand River and the Mississaugas of the Credit First Nation as compensation for their role in the war and for the loss of their traditional lands in upstate New York. Of the 950,000 acres granted to the Haudenosaunee, less than 5% remain Six Nations land, and only 6,100 acres remain Mississaugas of the Credit land. We thank the Anishinaabe, the Attawandaron, Haudenosaunee, and the Neutral peoples for hosting us on their land. I am glad to welcome you back to our virtually and socially distant studio here in the Mike Lazaridis Theater at Perimeter Institute. We'll be doing things a little differently this time, and I think you're going to enjoy it. We're excited to be joined by Manuel Calderón de la Barca Sánchez, a physics professor at UC Davis and the star of an amazing IMAX documentary called Secrets of the Universe. Secrets of the Universe was co-produced by and partly filmed at Perimeter Institute and is now showing on giant screens and in science centers around the world. The movie follows Manuel as he travels to leading scientific centers around the world and puts his own theories to the test at the Large Hadron Collider. And now, Manuel is joining us to share exclusive excerpts from the movie and chat with me about physics, filmmaking, and, well, the secrets of the universe. So we encourage you to join the conversation online. We're at Perimeter on Twitter, so please tweet your questions you have for Manuel or for our outreach scientists. And also stay tuned to the end of the talk for an announcement I'm so excited to share. Now, Manuel, it is wonderful to see you again. Thank you so much for coming back to Perimeter, at least virtually. I think the last time we saw each other was in Washington, D.C. at the Secrets of the Universe premiere at the Smithsonian. How are you?
I'm doing great. It's a pleasure to be virtually back this year so that we can discuss how things are going with Secrets of the Universe and to share some of that excitement with the public at Perimeter as well. It's wonderful to be here.
Well, we are grateful that you made time for us. I've been looking forward to this for a long time already. And also, maybe just before we begin, where are you beaming in from?
So I'm beaming in from UC Davis, and the picture that I have in the back is a picture of the compact muon solenoid, which is the experiment that I work on and that you'll actually see featured in the film. So we'll have some scenes where you see some of the animations they made with the collider detector being closed, and this is the facility that about 3,000 of us use to do our experiments at CERN. And the CMS is just one of the experiments. There's 4 all the way around the ring, but the one that I work on and the one that we featured in the film is this CMS compact muon solenoid experiment.
Oh, very good. Well, and I guess that also hints really well to we're going to do things just a little bit different. You picked some exquisite excerpts from the film that we're going to share, but just for our audience, these aren't really spoilers. This IMAX movie, it's in full 3D. When you see it on the big screen, created by Stephen Lowe, an unbelievable filmmaker, Canadian filmmaker, K2 Studios, an unbelievable group of amazing people in Los Angeles, Bob and Mark Kresser and Rob Lusk. It's an amazing film. You need to see it on the big screen. So these aren't spoilers, these are teasers. Is that fair to say?
Mm-hmm. I think that's very fair to say, yes.
All right, well, why don't we get right started? I'm going to hand it to you, whether you want to set this up or just roll the film. Over to you, Manuel.
Yeah, so I mean, for each of the clips, I kind of prepared just a little slide for just to kind of introduce what the clip will be about. And I kind of did it using also the kind of questions that I would always hear from kids, because one of the things that Stephen Loeb always made very clear to me was that, our target audience is this film should be understandable and hopefully should generate a lot of excitement among kids. And so So I always think about like, how would be what would be the kinds of questions that I would get from kids, and to make it communicable, understandable, and exciting to kids. So we can start just from the first slide. I don't know if you can show up the first slide to introduce the film, and the first clip is setting the stage for what we're going to be discussing in the film. And when we were discussing the story, Stephen Lowe, who's a wonderful director who always was very clear, like, we need a story thread, who are going to be our main characters. And I'm coming from the physics side, talking about the science, and we zeroed in on the fact that our main character is going to be the atom, and our the lead nucleus that we then end up using to collide. And basically the film tells the story about how do we understand atoms, and then also how do they came to be. And that comes to some of the very fundamental questions that we might ask as kids, like, what are we made of? And then what are the things that make those things that make us? So we can now just go to the clip, and hopefully we can then generate some questions.
Fantastic.
It was once thought that all things were composed of water, air, soil, and fire. But in the 5th century BC, the Greek philosopher Democritus proposed that all matter must be composed of something invisible. Long before the dawn of modern science, this speculation remains among the greatest insights of the human mind. The ancient Greeks called these tiny particles atoms. But where did they come from? And how did they come to exist? It is the ultimate question.
Wow, those are amazing animations. You can just feel it.
They are.
So I don't know where we want to start necessarily, but when I'm looking at that representation of an atom, I'm thinking not of just children, but of my rec hockey team, and how they would describe an atom is typically the solar system model. So
right.
Can you tell us why we need quantum thinking had to replace that old model just to even set the stage for where we're about to go?
Yes, I mean, very good question. I mean, the first ideas of the atom, originally they were, there was a big question as to how exactly the atom looks like, and even some of the very first ideas, there was a whole model that was called the plum pudding model, because
yes.
we knew that the atom had a certain weight and a certain volume, but we didn't know exactly how it was all distributed. And so people thought, well, there's the entire mass is kind of distributed everywhere, and that once the electron was discovered, then people realized the electron is 1 part in 2,000 the weight of even the lightest atom. So the electron has hardly any mass. So people were like, well, maybe this is kind of distributed in the entire volume of what the atom is. And it was through experiments like the experiments that we do now, essentially the first experiments that Rutherford did, bombarding alpha particles which at the time, now we know that these are nuclei of helium, bombarding them at nuclei of gold. Those were the first experiments that showed that this idea of the plum pudding didn't work, and that we now needed something really, really, really tiny and very, very, very massive at the center. And that's where the kind of idea of like the model, like a planetary model with the sun having most of the mass and then the planets orbiting around, sort of came to be. And as we started learning more and more about the how the atoms behaved, and we started realizing that there's a lot of things that a classical theory, which could explain things like orbits around planets, a classical theory could not explain. because in the atom, the orbits of the electrons had to have very, very specific radii, very, very specific properties, whereas nothing necessarily says that we need to have the Earth at a particular distance from the sun or Mercury at a particular distance from the sun. Those happen to be kind of accidents, so to speak. But for the atom, there is no accident. They have to have exactly the right properties. And every atom looks exactly the same. And that's what kind of gave rise to the idea of the language of the quantum. Like there's a quantum jump between those, and that quantum idea is an invented word that represented the fact that we needed these very discrete but very distinct and very exact distances between the various orbits and things like that. And that was one of the first ideas that led to the development of quantum mechanics. And so in the animation that we see there, the calculations that can be done as to what those shapes are. Originally, some of the very simplest ones could be spheres, but like all these funny shapes that you see in the animation come from actual calculations that use quantum mechanical equations to describe the where the electrons might be in their orbits on the atom. So that's one of the things that was already included in one of the first clips of the movie.
Thank you. And you know, you mentioned it in the setup, but it's probably worth digging a little deeper too. You and Steven chose the atom
yes.
as the base for the entire film. Can you talk a little bit more about that?
Yes, I mean, and I think, you know, at least for me, part of the brilliance of the idea is that it's something that when I talk to people, when people ask me what I do, the atom itself is one of the things that I find that it's a common thread that even people that are not scientists or physicists, it's something that at least you can encounter in school. And so I can latch on to that idea because they've heard about the atom, they've heard about the electrons, and they've heard about the fact that there's a nucleus, and they've heard the word proton and the word neutron. It's something that at least they've heard about. Because when we start talking about the point of the research that we discuss in the film, the existence of quarks and gluons and the strong interaction and the strong nuclear interaction, that's something that is kind of beyond the usual curriculum of what people hear in school, even like junior high or high school. And so we couldn't really start with that, but we wanted to start with something that was more familiar. And the fact that we start with the atom and the nucleus is kind of like the unifying thread around which we weave the story. But we can then, even when people are familiar with it, we can still ask, okay, how did the entire world around us that is made up of atoms, how did it come to be? Because at the very beginning of the universe, there were no atoms. So how did that happen? How, what was there before atoms existed? What was there before protons and neutrons existed? And this is part of what we're studying in our experiments. And so we realized we can connect that thread with starting from the atom, because the atom is something that's a bit more familiar. But we can still just asking one level down, we get to the questions that we're already studying. And if we even ask one more question, okay, now that we study the quarks, where do those come from? We get to the point that we don't know anymore. So just in 3 questions, we get to the limit of human knowledge. And we wanted to start with one part that was common to all, and to show that just you just dig a little deeper and you've reached our limit. And so it's fun to think about that too.
Oh no, that's fantastic. And just to our online audience, as you have questions after each clip, you send them in. The team will feed them right to my computer here, and I'll be able to ask Manuel. So keep the questions coming. Maybe one more question before we move to the next clip. And this step away a little bit from the science, you just so eloquently talked about the filmmaking process and why you landed on the atom. Why did you choose to do this? This was no small amount of work. It was an incredible journey that I was fortunate enough to be a small part on that journey with you. Why did you choose to do it?
I mean, I've always liked to communicate the science that we do. I think that that's one of the most important things that as scientists we can do. And not everybody is necessarily like keen on really taking on that role. But that for me as an educator is one of the things that I always that for me is a passion. And so when I got the opportunity to, like, originally I was not even going to be in the film. I was going to advice on the science, but just the fact that I was going to be involved in a project that was aiming to communicate science to as broad an audience as possible. Like, we're always thinking, okay, we can maybe communicate science to broad audiences, but a film that now we're talking, this can reach tens of thousands of people, like, whereas some of the efforts that we sometimes do when we say, like, we're going to reach a broad audience and we go and give a public lecture live, we can reach hundreds of people, but reaching tens of thousands of people with a film, that's a whole other ballpark. And so the moment that I got the chance for it, for me, I was like, where do I sign? What can I do? I'll be happy to do anything. This is amazing. And so for me, it was like, even though it's something that's difficult, but in terms of, like, taking such a challenging project, the rewards are so big that to me there was no doubt this is something that I want to be involved in.
Well, we are all grateful that you chose to do it. It's special. And just for a little plug for the film too, it has won several awards, and it is truly showing in science centers around the globe. So at the end, I'll explain where you go to find out local listings. But yeah, good stuff. Maybe we'll want to go to the next clip.
Yes, and so if you look in the slide that presents the next clip, we start to get to know the collider. And when people ask me always, like, well, what is a collider for? In one of the books that I read from Nobel laureate Leon Lederman, who was director of Fermilab, and he's explaining what it is he has a dialogue with Democritus, who was the person that came up with the concept of the atom. I liked how he explained it. He says, like, imagine that you have feta cheese, because Democritus is Greek, so he's talking about feta cheese, and you want to cut the feta cheese. And Democritus has this idea, like, is there fundamentally a limit as to how small you can make things? That's where the question that gave rise to his idea of the atom, the indivisible thing. And so Leon Lederman says, guess what? We're going to make the biggest cheese cutter on Earth, the biggest thing that will, that can break down the feta cheese to really its tiniest components. So that's what our collider is. It allows us to really get down to the smallest components of matter. And so we can look at the clip now.
Good, nice.
I'm back in Geneva for the next few weeks to work with the Large Hadron Collider. 27 kilometers around and buried on average 100 meters underground, it is the largest scientific instrument ever built. With it, we will seek to look back in time to the very beginnings of the universe.
And well, I've had the fortunate pleasure of visiting CERN a few times, and I am always just so impressed by the enormity of the LHC. So, and I know we'll talk a little bit more about the physical details of it, but can you talk to us a little bit about what did it feel like to be sitting at the world's most complicated machine to do your experiment?
I mean, that always is a humbling experience. And for me, and I mean, I've been working at some of these facilities for over 20 years now, and it's still a thrill every time I go. And one of the things that I always ask, whenever I have a grad student that's new that is going to go there for the first time and might spend some time going there, because it's sometimes not easy to get access down to see the detectors and to get into the tunnel, because when the LHC is running, basically you don't have access because of the radiation danger and things like that while the machine is running. But like when there's an access because they might need to come in and fix something, and the accelerator stops for a little bit. I always tell them, like, make sure to get all the training that you need to get down so that you can actually see the detector, because I can show you pictures, I can show you but there's nothing quite like seeing the scale of it. And that's one of the reasons why I also wanted to do a film like this one, because it is the next best thing. I mean, these detectors are 5 stories high, and the IMAX screen is 5 stories high. So then when people said, like, we can actually show this life size, then that's the next best thing. As you say, it's a privilege to be able to visit these facilities. But not everybody can actually go and visit CERN. And even if you do, you might not be able to go down because they might be running. Yeah. And so to be able to get an idea of the scale, the right medium is the IMAX screen. So that was another reason why I was really excited about making a movie like this, because there's, you can at least get the sense of the scale with the imagery at the right size, having that kind of screen.
Yeah, that's a really good point. And while we are talking about the scale of it, I know we have more details of the actual collider coming, but just briefly, why does it need to be so big?
Good question. There's two scales of bigness here. There's the scale of bigness for the collider itself, and then of course the detectors. But since we just talked about the collider, let's talk about the collider itself. The thing that determines how big you need to make it is twofold. Like you need two things to make the collider work in terms of, like, how much you accelerate, how high energy you accelerate. You need electric fields, which are the ones that essentially push the particles along. And so you can, as long as you can keep putting more and more and more, or push them more and more and more, you can keep increasing the energy. And there's usually two designs. There's a linear accelerators, and all that means is that you just need a very, very long straight section, and you just keep putting more and more and more, essentially batteries, just sophisticated batteries, but ultimately batteries, so that you can have electric fields that just push the particles along. And for the case of a circular accelerator, the advantage is that you just need to put the batteries or the electric fields in one place, because you then send the particles around and then push them again, and then you send them around and then push them again. So then the limiting factor becomes what you need to send them around are magnetic fields. The magnetic fields simply bend the particles and keep them in a circle. But the larger the energy, so if you keep pushing them and pushing them and pushing them, increasing their energy, you need higher and higher and higher and higher magnetic fields. So that is the determining factor. Right now, we are at the limit of what our technologies are able to provide in terms of the strength of the magnetic fields that exist at the LHC. And one of the facilities in which we filmed was where they're doing testing to increase the strength of the magnetic field, because that's what will allow us to make even higher energy accelerators, hopefully, in the future. But those are the two things that really determine the size of it. The strength of the magnetic field is mainly right now our current limiting factor.
Oh, well, thank you. And we just had an online question from Sarah, and she just asked that exact question. Are there other colliders, bigger colliders on the horizon? So I guess.
So they're on the horizon. CERN itself is thinking of making, so as we mentioned in the clip, the Large Hadron Collider is in a tunnel that is 27 kilometers around. So something like 17, 19 miles, something like that. Or yeah, 27 kilometers around, but they're thinking of making a 100-kilometer ring. So making it bigger means that you don't have to bend as much, so you can use magnets roughly of the same. So even if we use the same magnets, with a larger ring, we would be able to accelerate them to higher energy. But if we are also able to increase the strength of the magnet, that would also give another factor in terms of the energy increase. So that is what is currently being discussed. But of course, that is, for that to be built, it's probably going to be a few decades before it actually gets built.
Oh, very good. Thank you. And just before we leave this clip and move to the next one, CERN, it's a talent magnet for the globe. So can you talk a little bit about the team that you've put together that is doing the work with you?
Yes, I mean, the CERN is, as you said, it's one of the biggest and most international physics labs in the world. I mean, it was born as an international collaboration from the get-go. I mean, there's also big labs, for example, in the United States, and there's big labs in China, but CERN was born as an international lab with many states contributing. And the accelerator is so big that it really needed not just the member states, but people or nations that were not just in Europe, because of, the name CERN has the E for European, but there's many nations that are not European that really contributed a lot of funds for this to happen, and they're also contributing with people. So there's on the order of 10,000 scientists working at CERN, and in my experiment, there's like 3,000 people just working in my own experiment. And they really come from all walks of life and all sorts of nations and all sorts of backgrounds. And that's one of the things that I love about CERN, that you really feel that sense that we are all here coming from as many nations as you can think of, with even though we have many cultural backgrounds, we have a singular purpose of just advancing human knowledge, which is a really, really, utopian and good thing to think about, that there still are places where many people can come together from all sorts of backgrounds and have a higher goal that is really something that we can all get behind. So it's one of the things that makes me very, very happy to participate in the science at CERN.
Oh, fantastic! Why don't you set the next clip up? Yeah.
So for the next clip, so you can look at the slide that sets it up. One of the things that we study when we collide the nuclei that we'll be talking about, called it the primordial soup, because it really is where all the rest of the atoms come from. And that was one of the things that we wanted to test. People thought if we have these collisions at very high energies, we might be able to create this quote unquote primordial soup. In other words, we would be kind of going metaphorically backwards in time to produce what existed a microsecond after the Big Bang. And so that's what people were thinking we could do. The question is, would we be able to do it? So let's show the clip.
One idea suggested we could simulate a moment in time when atoms had not yet formed. It would become one of the most ambitious scientific experiments ever undertaken. A journey to the most distant edge of the universe in both time and space. 14 billion years closer to the Big Bang. A moment long before our Earth and solar system were formed. A journey back to the quark-gluon epoch, a time and place too hot for even atoms to exist, where subatomic quarks were thought to be held together by a mysterious force, the strongest in the universe.
Oh, that's great graphics. But before we get into the quark-gluon plasma, that scene opened with a really awesome shot down above that group of collaborators at a table. Of course, that triggers me because that was shot at perimeter.
That was
on a perimeter table. But
yes.
so,
and I love those tables. Those were one of my favorite things about that was like you can have lunch and then you can still just be writing down all the ideas on the table. It's brilliant. I love that.
Oh, thank you. Yeah, the collaboration here is deep and real. And the part that I think would be worth pulling on the thread a little bit is Perimeter is a theoretical physics institute. It's theory. It is chalkboards and coffee. You're an experimental physicist at the largest experiment on the planet. Can you talk about why it was necessary to have both experimental and theoretic physics in the film?
Absolutely. The way that I see it is that this is as scientists we need both in some sense. So science. We need the world of ideas to try to kind of make sense and think about what might nature be telling us. But ultimately, we also need to check whether nature indeed is saying what we think she is saying. And so the experimentalists are the ones that are trained to check and probe nature to obtain a measurement that can hopefully, it doesn't always happen in such a clear-cut way, but the hope is that you do a measurement, and that can lend evidence to a particular way of thinking, or in the best case of science, which is something that always people don't necessarily think about. It's not that an experiment necessarily proves that something is right; it rather like it's consistent with it. But what an experiment can also do is that it can prove that something is not right. And so if you have a theory that then says this is what should happen, but experimentally that doesn't, then that's it. You discard the theory. And that's what has happened with many a theory. But and that's kind of how we advance. We have all these plethora of options, and we kind of narrow down to what are the still viable options that we haven't been able to rule out. And and that's kind of why we need both worlds. That's how the whole science, the whole scientific endeavor advances. And in physics, it has become so specialized that you need the people that specialize in the world of ideas and probing the math as to what is it that a particular theory is going to then say. And you need the people that specialize in working with the detectors and working with the machines and working with the data analysis, because it's a very complicated thing to work with this massive data sets and to make sense of the data to figure out what is nature trying to tell us. So we definitely need both, and it becomes a feedback and a feedback loop, and as the various ideas from each of the camps gets traded back and forth, so that we can then advance in terms of our knowledge of how the world works.
Oh, love that. That is the process of science perfectly shared with nature as the arbiter. I love it. Love it.
Yes.
So here, an online question. The clip that you shared described your research almost like a form of time travel. Are you using the LHC to essentially recreate conditions of the universe as it was billions of years ago?
Yes, we are essentially using the LHC to recreate the conditions 1 microsecond after the Big Bang. And but I also want to point out that this is not the only place where this can happen. It's just that this is a place where we as humans can recreate them in a controlled way, so that we can actually take pictures of it, and so to speak, or like use our detectors to gather data and study it. But this is, these are processes that are happening in other parts of the universe as well. It's just that we might not have access to those, because they might be happening in exotic places, like in the cores of neutron stars, or they might be happening in the collisions of 2 neutron stars, or in a supernova explosion, or something like that. Where some of these things might be happening, with some of these states of matter that we are looking for might still exist nowadays. But what we do think is that the reason why we say, like, we're kind of quote unquote metaphorically traveling backwards in time, is that for the temperatures that we're reaching in these collisions, those are the temperatures that the entire universe, not just localized spots, but rather the entire universe existed in this state around those times, 1 microsecond, 1 picosecond after the Big Bang. And so that's why we say we're recreating the primordial soup, because that's where this is how the universe was before atoms existed. So yes, and so hopefully that helps clarify and cement that metaphor.
Oh, that's good. We have so many good clips to get through. Let's set up the next one.
Mm-hmm. And so in the next slide, if I can show the next slide, we kind of start talking about those concepts that that go from the small things, the atoms that people know, to then the protons that people might have already heard, to quarks, which is, in my experience, something that not everybody has always heard. And the interesting thing is that, to me, that's just like going one more level down, which I would advocate that this is something that we should also be teaching in the high school level as well, because that is, once you get to that level, as far as we know, there is no smallest thing. So in some sense, the quarks really are the correct indivisible, the atomos that the Greeks were thinking about, as far as we know. Maybe at some point we'll discover that there's something smaller than that, but as far as we know right now, these are the smallest things. So the next clip kind of discusses going from the atom to the proton inside to look at the quarks.
All right.
Here at CERN, we study the tiniest particles in nature. The hydrogen atom is the simplest of all. It has an electron spinning around the outside. If you pass through the electron cloud, continuing towards the center, you would find a single proton. Inside are 3 quarks, held together with the strongest force in the universe. For us, understanding this force is the holy grail of physics.
Manuel, did you find, this from a sort of an outreach educational perspective, did you find that the working with Stephen and Pietro and that team that you were able to use incredible animations, did that help you bring the science to a new level? Or was it sort of just a nice melding of art and science, or a little bit of both? How did that play out?
I mean, I think it's a little bit of both. It's because some of it is trying to visualize things that that are difficult to visualize because we don't really see the quarks directly. But we do have an idea as to how they're supposed to be interacting based on the calculations done with supercomputers. But ultimately, we have to put them in a film. We have to try to get some of that science and convey that in a way that is visual, and that we and conveying all of the things that we think are the correct representation of what we know now. So that was a big part of the dialogue, like trying to put this in a way that could be visually appealing, but at the same time scientifically accurate. And so we strive to try to do that. It wasn't necessarily always we didn't quite get all of the science in there, but we got enough of it that everybody that has seen it, including, because I was always worried, at some point we would be doing things, and I know that the audience is not other physicists, but that other physicists that have seen it have been really pleased with how accurate things are in terms of being able to represent things, and not kind of tone it down or water it down. Like, things that we say are really all scientifically accurate but understandable. Like, that was the hope, and that was a challenge, and we really worked hard on that. And for, at least from the feedback that we've gotten, it seems that people have resonated with that kind of approach.
There's an online question that probes that a little bit, that question exactly, assuming the director, Steven, isn't a scientist, but an artistic wizard, and you, the scientist. So describe a little bit of that tension as you created this film.
I mean, it was actually for me, it was a pleasure to work with Steven, because he has the that kind of instinct and the curiosity of a kid, and he said, like, this is I'm thinking about kids, right? And so he had, I told him, like, you can ask any question you want, and he would have, like, he was like, yeah, maybe this question is like, no, this not, there aren't questions that are dumb or anything. All questions are valid. And so we would just have hour-long conversations on the phone, where Steven would ask me, like, how are things working, and I would try to explain how this or that worked, and the lead nucleus and the quarks and the gluons and things like that. And we would spend lots of hours on the phone trying to make sure that he understood. But also, a big part of the component of it was not only did Steven want to strive to understand the big picture, and he understood the various complexities, but to then turn those complexities into a simpler thread that we could then use as the narrative for the story. And so it was. And as he came up with the ideas, okay, this is what I'm thinking as a narrative, and this is what we want to present here and here and here. Is this scientifically okay? And so there was a lot of back and forth then between us, and in terms of me explaining the science, and then him sharing what he wanted to do with the film, and making sure that we were saying things that were scientifically accurate, even if, like, ultimately, like, for example, he said, like, we are going to make a story that is not necessarily going to be a full documentary, because it's not necessarily that we're really following step by step what you guys are doing in the exact same timeline, but it still is going to tell the story of what you guys do in general, and that's what we want. And so it was a very rewarding process for at least for my side. I felt like it was like I worked really well in terms of making sure that we really conveyed something that was both truthful and exciting and understandable. All of those things together, we really strive for. And I working with Steven was just an absolute pleasure.
That sounds great. Just before we move on to the next clip, you mentioned in that clip the holy grail of physics. So understanding the strong force for you and your team would be the holy grail of physics. Can you just briefly tell us, why would that be such a breakthrough?
For me, it was, it's always interesting to think about the fact that, we are trying to understand the fundamental forces of the universe. the strong force, the force that is the one responsible for the quark and gluon interactions inside the protons, is one of the forces that we've known about for the least amount of time in human history. We've known about gravity since the very, basically since humankind essentially were humans, we've known about gravity. We've known about electricity. I mean, the word electron is a Greek word. So since the time of the Greeks, we've known that if you rub amber, that's where the word electron actually comes from amber. So the Greeks would rub amber and they would realize that there's some funny force that you could feel if you rub two pieces of amber and bring them together. So we knew that there was a force there, and it took us a while to figure out what this force was. And in the 1800s, we have Maxwell laying down some of the laws of electromagnetism. And then in the 1940s, we got a quantum theory of the electromagnetic field. But it's something that we've known about for a while, and it took that long to develop and understand this. And then just to give kind of the analogy of where we are with the strong force, we've had a theory of the strong interaction since the 1970s. So, and since in the 1960s is when we got our first glimpse that there was something that we needed that happened when we started colliding protons, and there was something that's inside that is strange and that we need something new for. So, in one human lifetime is basically the span of the strong interaction and how much we know about it, and yet it is the strongest of all the forces of nature. And so, to me, it's like it's a really kind of funny thing that it was hidden inside protons and neutrons, and therefore we were oblivious to it for essentially most of our history, and we're just starting to figure out how it is and how it works. So that's what I meant. Like we're just like this is the strongest of all the forces, but it was hidden from us. So we're revealing the secrets of the universe that were kind of in this nugget inside the atom. And so that's why, to me, it's so exciting.
Oh, that's fantastic. Let's set up the next clip. Go ahead.
So yeah, in the next one, we are going to go inside the collider, and we describe some of the properties that the collider has, and it is really literal that this is the coolest thing, and the emptiest thing, and one of the biggest things that we've ever made. So that's what this clip is about. So we can go to the clip.
Inside these two vacuum pipes will travel beams of particles going in opposite directions and accelerating to near the speed of light before we smash them together. Each section of Large Hadron Collider pipe contains very powerful magnets. They keep the particle beams perfectly aligned to collide with each other. We hope. The Large Hadron Collider is in effect a 27-kilometer superconductor. The pipes are also held at a very high vacuum, emptier than interstellar space.
Those magnets always amaze me. And I have here, this is some of the superconducting wire wrapped in those magnets. And folks it's braided, it's flat, but it's braided superconducting strands. Can you connect the dots for us? Why do we need superconductors in those ultra-powerful magnets?
The superconductors are needed because you essentially are putting in a large current through the cables, and the larger you can make the current, that is what creates the magnetic field. So in other words, these are not permanent magnets, these are electromagnets. So you need to basically send a large current through it. And you could do it without using superconductors, but then the electricity bill for doing that would be humongous. It would be through the roof, because there would be a lot of losses due to the resistance inherent in any material that is not superconducting. So making them superconducting allows you to really conduct electricity with no resistance. That is the definition of a superconductor, and that means that you don't have heat losses, and you don't have other losses other than just creating this humongous amount of current that produces some of the largest magnetic fields. And so that's why we use superconductors. Likewise, in the detector to produce large magnetic fields, our detector also has a huge superconducting magnet. And it actually is, I think, in terms of its size, the largest superconducting magnet in the world. And so we use superconductors for a lot of what we do.
All right, and here's another online question. It says, what do you mean when you say emptier than interstellar space, and why is that necessary?
Very good question. Vacuum. So when we say that we create a vacuum, no vacuum is ever perfect. There's always some trace amount of particles, and so we can actually measure the pressure, and the pressure it's never exactly zero. So you can have things that are very low pressure, but they can be in units of an atmosphere. You can then say maybe have 1/10 of an atmosphere, or you might have 1/1000th of an atmosphere. And so there's a particular value that interstellar space has, and it turns out that the vacuum that we produce at the Large Hadron Collider has a lower pressure. There's less particles around than even interstellar space. So that's what we mean by emptier. You can actually measure the pressure and how many particles there are floating around in a given amount of space, and we have less particles floating around in a given amount of space than there are floating around in interstellar space. And the reason why we want that is that as we're sending the beams to collide, they're going through each of these pipes. And so imagine if you didn't have a vacuum and you just had regular gas like air. Well, those particles would be colliding with the nuclei of the atoms in the air. And so then you would be spraying out all the particles in all sorts of directions, and you would have lots of beam losses. And we actually can detect, even though we have a very, very, very good vacuum, like I said, it is never perfect. So we can still see examples of in our detectors of collisions that happen to be between a particle of the beam and one of the particles of the gas that remain within the vacuum pipe, because the vacuum is never, you never get down to exactly zero pressure. There's always a few particles flying around. So that's what I mean by that. Hopefully that answers your question.
Oh, that was great. And you know what? Talking about particles in the beam, maybe let's go to the next clip.
Yes. Yeah, so the next clip is discussing how we actually reach the energies and how we then guide them to smash the various nuclei, and how we then accelerate them. So let's show the clip.
We're going to try to collide massive lead ions, atoms with their outer electrons stripped away, 200 times heavier than earlier experiments. We will accelerate these lead ions to the highest energies achievable on Earth, passing them from one accelerator to the other, each one increasing the energy of the ions. When they enter the largest accelerator ring, they will be traveling so fast, they will be a hair's breadth from reaching the speed of light.
I love that.
Yeah, I love that.
So there's an online question I'm going to get to, which is a fun one. But first, let's talk about the 200 times. So you're using lead ions instead of protons or helium nuclei. Mm-hmm. Can you tell us a little bit about why you need to use the heavier ions?
Yes, and part of the idea is that what we're trying to do is we're trying to recreate the state of matter in which the universe existed, as I mentioned, like a microsecond or a picosecond after the Big Bang. And when we are talking about recreating a state of matter, and changing nuclei from the regular nuclei that we know into this plasma of quarks and gluons that is this new state of matter, you want to do that using as many particles as possible, because it is akin to saying, well, I want to change water from being a solid to a liquid. And if you want to study the change in the phase of matter to create something new, the way that you do that is you have to look at the behavior of a whole assortment of molecules. You don't just look at one water molecule and then decide, is this water molecule ice or is this water molecule water? The one water molecule can't tell you that. You need to look at a huge ensemble of them to then see how is the ensemble behaving. And so the more particles of that object you're trying to study, the more particles you have, the better, because then you can really study, is this a particular state of matter, or are they behaving in a different way? But it's many of them. And so what does that mean for us? If we accelerate a proton, there's going to be only very few quarks in there. But if we accelerate a bigger and bigger and bigger nucleus, that means we can collide all of those quarks together. And then we can get as big a state of matter as we can. I always used to joke that if we had the budget and the technology, we would be colliding neutron stars in our experiments. But we don't have the budget or the technology for that. But we can get as big a nucleus as we can, and that is why we get things like lead, because they have 208 protons and neutrons all stuck together. And boom, then we collide them, and that's as big of a nucleus as we can get. And of course, there are bigger nuclei, but one of the advantages that lead has is that it's simpler because it's very spherical. And so that allows us to, like, if you have a funny shape, you can then have to worry about the complications of a non-uniform, non-spherical shape colliding, but using spheres makes things a lot easier.
Oh, very good. Okay, so here's the online question, a little bit of a fun one. There are some unconventional theories out there that the Large Hadron Collider is going to accidentally or deliberately create a black hole that will swallow us all. Do you encounter such ideas, and how do you respond if you do?
Yes, and yes, we do encounter such ideas, and this is not the first time that it has happened. Like when I was a grad student and the Relativistic Hadron Collider in Long Island, in New York, was about to start, we had the same kind of discussions, and the one of the ways in which you can realize that this is, essentially, as I mentioned earlier, what we're doing is not something that nature doesn't do by herself. The types of collisions that we have here are happening in different places in the universe. And in particular, and this is something that particle physicists know very well, that the energies at which we are colliding are not really the highest energies that we can access. When we study cosmic rays, for example, the protons that are coming from cosmic rays, and sometimes there might even be heavier nuclei that collide with the particles in the atmosphere, they can do so at energies that are orders of magnitude higher than the energies available at the LHC. And these cosmic rays are bombarding us, they're bombarding the moon, they're bombarding all the planets all the time. And then they've been doing so since way before there were humans, for millennia, for millions and millions of years, at energies much higher than anything that we can create in the lab. So that's why when we say we are colliding things at the highest energies achievable on Earth, well, in a collider, in a controlled environment where we can produce millions of them in the same spot. But there's collisions that are happening that are way higher energy than anything that we can produce on the moon and on the Earth in cosmic rays happening all the time. If we're still here, that means that all of those collisions are not going to destroy the universe, because they're still happening. That cosmic ray probably just passed right through me, and probably just passed right through you. If you just wait long enough, you wait a few seconds, probably another cosmic ray just passed right through you. And some of that is coming from the collisions that are happening in the atmosphere or in other planets. And yet they have not created a black hole that is going to swallow the universe, because otherwise we would have already been gone. So we know that these types of collisions are not going to create some catastrophic event, because they're happening around us all the time. It's just we don't have a detector to detect them. Here we have a detector because we're going to produce many of them so that we can actually study them.
Oh, thank you very much. Let's move to the next clip.
Yeah, so now we're getting to that idea of what we're trying to do, which is create a new state of matter. And when we say new state of matter, I like this idea of, the solid to liquid, because that's kind of what we're doing, trying to melt the proton. If the proton is the equivalent of our solid, we're trying to produce a new state of matter that equivalent is kind of like melting the proton. And for that, we need to raise the temperature. So the clip tells us a little bit as to how hot do we need to make things. So let's look at the clip.
When two of these tiny giants collide in the CMS detector, we expect a temperature 100,000 times hotter than the sun. a quest to understand the microcosm, a journey that began centuries ago.
Manuel, when I see that, and when I first saw that clip that you're going to use, it made me think, what does it say about humanity that we can theorize that was an actual reality, that we can then mathematically model it, then we can design and build an experiment to create it and then test it? What does that say about humanity?
I mean, that to me is one of the things that gives me hope about humanity, because of course, there's as you look at the news, sometimes you see so many things that are are stressful about the status of humanity. But the fact that we as a human race can really think long term about, like, we're trying to understand how something works, and it really is just our innate curiosity for understanding how the universe actually works. And that we're able to do this, and that we are able to put resources and value into just understanding, knowing that maybe some of what we learn might not necessarily have an application. A lot of applications, of course, have come out of that, but that's not primarily why we do it. We do it because of the innate need and curiosity of finding out how the universe works. And the fact that we're able to do that is indeed some of the things that really fill me with hope for our future, for sure.
Yeah, that's so true. I have an online question which sort of probes that next question. Do you intend to do more experiments at the LHC? And if so, what?
Yes, I mean, one of the things that we don't necessarily touch a lot upon in the movie, because like the movie has to have the thread where we say, like, you have a question and you kind of have an answer. But science is like when you're looking at that, like what the scientists are doing, it's every time that you do a study, that study always kind of like raises like 10 more questions. And so then that's what we do. Like, we know that we have been finding that, yes, maybe this state of matter is formed. Well, now, okay, what are its properties? What does it do? Like, how does it work with this particular particle? How does it work with this other particle? What happens if we raise the energy? What happens, when can we turn it off? How low can we go until we stop seeing it? And so there's all these questions that a scientist asks because they really want to understand how exactly it works. So science is never simply, it can be, does this exist or not? But once you find that something exists, well, you want to find lots of things about it. And so part of what we're doing is trying to understand, okay, yes, this exists. How does it work? And so there's lots of questions that are surrounding that. How does it work? That will take decades to unravel. So this is we're summarizing in the film over 20 years of work. And of course, there's going to be more to come, because we have plenty of follow-up questions that we want to ask. But that's kind of that's in all fields of science, that is the case.
Yeah. Let's go to that final clip.
Yeah, actually, we have two more.
Oh, excellent.
But so this next one, and the first one is shorter. The next one is a little bit longer. But this one is talking about what is it that we use to take all the data, to take all the pictures of our particles. So this introduces and shows what the detector looks like.
We're about to fire up the greatest time machine in the history of the world, becoming time travelers, going back further than ever before, to within a millionth of a second from the beginning of the universe.
That's incredible footage. So do you want to talk,
yes.
we are getting a little tight on time, but do you want to talk a little bit about what we were looking at there? What was closing?
Yes, so those were the two halves of the compact muon solenoid, which is the same picture that I have behind me. It's a whole suite of many detectors that we use to basically take pictures. These are now three-dimensional pictures, but we obtain the visualizations for us to study the data, but also we obtain much more than just the pictures. We obtain like the information as to the energy of the particles and where they're going, where were they in space, and that is what we used to do essentially all the science and the studies all the thousands of people that are working on it use the data coming out of those detectors. So for us, these are our workhorses, the actual detectors that can look at the experiment.
And
the collisions.
that's the 5-story high CMS detector. That's what we're looking at.
That's the 5-story high. Yes, that's a 5-story high CMS detector, the compact muon solenoid. Which I always laughed about the fact that it's compact because it's 5 stories high.
Oh, very good. All right, let's take a look at that last clip.
Yes. So this is kind of like the end of the story, where we actually look at the collisions and see what happens once we saw the collisions. So let's roll the clip.
A range of cross-sections that you can use, and depending on what button.
Just as quickly as it started, it's over.
On the previous
Oh,
page.
the one with no loops, right? Yeah.
Before the collider has even stopped, the chant begins. Did you find anything? I think it's fair to say we found everything. Exactly what the collider was built to do. The experiment has proven the theory of the quark-gluon epoch. A lost world, a millionth of a second after the Big Bang. We were not prepared for what we found next. 7 million miles across, with a temperature 1 million times hotter than the sun, we found a strange plasma, more liquid than water, held together with the strongest force in the universe. A boiling cauldron of tiny immortal quarks, the purest form of matter possible, a perfect fluid, waiting to form the universe to come.
Manuel, that film is designed and is currently inspiring not just children, but certainly children across the planet. Can you talk about what inspired you to become a scientist, and could you have imagined being in the chair you're in now?
No, I could not have imagined being in the chair. I mean, it's a dream come true for sure. And I mean, part of what inspired me, I mean, I didn't, growing up when I was in high school, I did not know that you could do science as a career. But it was in high school that I started learning physics and math and seeing how cool it was that, as I had questions about how the universe worked, that ultimately that's where I realized that whenever I asked, like, how does this work and why does this work this way, ultimately the answers led to physics. And then I also saw that if you put your mind to it, you were able to kind of understand how things work based on the work that so many giants had done before, but that you could understand how this worked, and that based on one idea, you could then explain so many different things. So to me, like when I first started seeing like even some of the simplest parts of the introductory physics curriculum, like when we started studying mechanics and Newton's laws is essentially one equation. And then you can spend months and months and months talking about applications of how this works in this situation and that situation, and it's all coming from the same idea. That kind of universality, how it applies everywhere, and also that idea that, as a high school student, that you can be talking about history, and then depending on which country you are, the history might be different. But if you were talking about physics, the physics is the same for everyone. So universality in that sense, in the sense that it doesn't matter where you come from. It doesn't matter what country you're from. It doesn't matter what planet you're in or what galaxy ultimately, that we all would be studying the same physics. That idea and the fact that we're able to understand it was something that really, really resonated with me. And little by little, I understood that, yes, one can actually pursue this as a career. And when I found that out, I was like, what? You can do this? And the first time I heard about the LHC, I was like, I want to do that. But it felt like it felt like an impossible dream. So the fact that we're able to do this now, that I was able to get to the LHC, and now, that's one of the reasons why I feel like I love paying things forward, because I still remember the feeling of awe and the feeling of utter excitement that I would get when I would find out something new and that it would make sense. And I want to share that with as many people that might then get that same bug. So it's just a privilege and a pleasure.
Well, thank you. We are just about out of time. I would like to we do this typically with our public lecture guests. We do a speed round. So it's like one word or a quick phrase answer. Are you willing to play?
Sure, absolutely.
Okay, so here we go. Where's the next exotic place you'd like to conduct research?
New Zealand.
Ooh. What's your favorite particle other than the quark?
The gluon.
Fair enough. One scientist, dead or alive, you'd most want to meet?
Maria Geppert-Mayer.
Scientific development you're most excited to see?
Room temperature superconductivity.
Ooh, and follow up, when do you expect to see it?
Sometime in the next decade would be great, but I don't know if that'll happen.
Biggest influence on your career, scientific or otherwise?
Some of my, probably quite a few of my high school and college professors, because those were my very first scientific role models. Yeah, for sure.
And last one, if you weren't a physicist, what would you be?
An astronaut.
Oh, nice. Manuel, thank you so much for taking the time to join us and to share and give us a glimpse into what is an incredible film. Those of you that are interested, there's at secretsoftheuniversefilm.com. You can get all the information about the film and also local listings around the planet. So that's all available to you. Now, and before you disappear, Manuel, I have a little announcement, and then we'll say goodbye in a couple seconds. So, for our online audience, as I mentioned off the top, we're excited to share that starting in early 2022, we're launching a series called Conversations at Perimeter, in which two co-hosts will talk to different fascinating scientists each episode. This evolution of our long-run public lecture series will continue to be offered on our YouTube channel, but it will also be available in podcast form and on all major podcast platforms. So we've already started recording these conversations, and we think you're really going to enjoy them. Stay tuned in early 2022 for Conversations at the Perimeter, and please subscribe to our YouTube channel and click that little bell in the top so you'll be alerted when we release new episodes. But until then, thank you for watching all, and Manuel, thank you so much for taking the time. It's been incredible. Thank you.
It was a real pleasure. Thank you very much.
Take care, all.